All right, hello. We're back for another homework. Great sequence of videos here. We are going over the 10.4 homework. What was the 10.4 section about? It was about basically isomorphisms. We had a pretty chill class that day. This was now maybe only like a week and a half ago that we did section 10.4, and yeah, it was some crap about adjacency matrices and incidence matrices and degree sequences, and we talked about what an isomorphism really is, and then we talked about polyhedra. Well, it was a homework, and it's kind of hard, I guess. I don't know if it was hard or not. Let's do it right now. Putting so much preparation into these lectures, into these little videos. They're helpful and professional. Woo! Go me, teacher of the year. Page 622 from Gossett. Number 1, for each graph, produce the adjacency matrix and the incidence matrix. Okay, I didn't really want to do this, frankly, but I'm going to do it. What do I have here? I have a graph with 5 vertices. And so, what is the adjacency matrix? It's the matrix which tells me for every pair of vertices whether they are adjacent or not, and with how many edges. But here, this is a very simple graph, so simple you might almost say it's boring. So these are all zeros because it's a simple graph. There are no loops. Here we have A connected to D and E, and that's it. Here we have, let's see, B is connected to D and E as well, and not to C. C is connected to only E. D is connected to only A and B. What have I done here? A and B. This is not the most efficient way to do this, but okay, too bad. And E is connected to A and B. So that was, I think that's just like wrong even. Let's see, E is connected to A and B and C, yeah. Okay, so it didn't really make use of various things, but there it is. Okay, good. That's the adjacency matrix. Well, what is the incidence matrix? This is just meant to introduce this concept to you sort of loosely. In an incidence matrix we have, let's see, is there a particular order that he wants us to do it in? I guess it doesn't really matter, but C, D, E, and then up here we have the edges, E1, E2, E3, E4, E5. Well, I guess there's not that much work to do because there's so few edges. What is A? Or what is edge 1, I guess? It's the edge between A and D. So 1, 1, cha, cha, cha. What is edge E2? It's the edge between D and B. So cha, cha, boom, boom, boom. What is edge 3? It's the edge between E and B. Boom, boom, boom. Yeah, good. E4 is the edge between A and E. Sha, sha, sha. And E5 is the edge between E and C. So, all right. This didn't really make my life better or anything, but it is true that there are some of the numbers in every row of this instance matrix is the degree of that vertex. Check, 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 and check. And the sum of the numbers in any particular column is going to be 2 because every edge is incident with precisely 2 vertices. So this would be a nice way of storing a graph in a computer so that you could perform graph things with it. Good. More. Produce the degree sequence for each graph. Well, this is just a straight up do it kind of problem. Here are the 4 graphs of exercise 1. Let's just make the degree sequence with the graph. What do we see? Well, it's quite freaking boring, in fact. Every vertex in this graph just has degree 2. Done. B. This is this thing, right? So what do we have? 3, 2, 2, 2, 1. Done. Here, what do we have? This, notice, is multigraph. And so, what do we have? We have 2 vertices of degree 4. Check, check. And then 2 vertices of degree 2. Done. What do we have here? Every vertex of degree 3 is just a cube. So that's 3, 3, 3, 3, 3, 3. There are 8 of these, 1, 2, 3, of course. So I ran out of space, so I'll just like do that. All right, done. Moving right through this thing, I'm gonna go downstairs and do some childcare. Create a graph with degree sequence 4, 3, 2, 1. Well, sounds pretty hard. In fact, you might be thinking, impossible. Because you might be thinking, wait a second, if the degrees are 4, 3, 2, and 1, it must mean I have 4 vertices. And if I have 4 vertices, then one of them must have degree 4. Well, how could this vertex have degree 4? Because there are only 3 other vertices that can possibly be adjacent to it. Aha! There is no simple graph with this degree sequence. But no one said this graph had to be simple. And so maybe I want to do that. Boom. Boom. And then what do I need to do? So I got degree 4 here. 3, 2, 1. So I think if I just do like this, am I just like done? Yep, I'm just done. Okay, 9. Produce 2 graphs with degree sequence 4, 3, 3, 3, 3. Okay, I had a feeling that are not isomorphic. I had a feeling that this was going to be hard, so I did it in advance, and I spent an embarrassing amount of time thinking about this, and I came out of it with deep understanding. So I pretty much just kind of went at random and tried to draw a graph with degree with 4, 3, 3, 3. In fact, maybe it's even good if we just like do this, right? Watch this. Take a graph with 5 vertices, which of course this one has. One vertex has degree 4. So if one vertex has degree 4, then it must be connected to every other vertex. And now at this point, like, there's nothing more to do, right? Because here I have a take this vertex up here. Well, it needs 2 more edges, and so, well, basically of these 2 vertices, you know, it must be incident with, it must be adjacent to 2 of them, and now there's only one possible way to finish this off. So that was kind of a proof, if you were paying attention, a very hand-wavy proof, that in fact this is the only possible graph with degree sequence 4, 3, 3, 3, 3. And actually, it is the only possible simple graph with degree sequence 4, 3, 3, 3, 3. But after trying for 5 glorious minutes to find another graph that was not isomorphic to this one, I started to think that it was impossible. But then I remembered, oh, it doesn't necessarily have to be simple. Is there a graph with this degree sequence which is not simple? Sure. Watch. You can make it be like K4, in which every vertex has degree 3. So jump, jump. And then you just have some random vertex out here with degree 4 because you just give it 2 loops. Aha, this is a disconnected and disconnected multigraph. But it's certainly not isomorphic to this one. So there we go. Woo! So 9 done. Oh, right. Produce an isomorphism for the pair of graphs, or explain why the two graphs are not isomorphic. A click and drag tool such as Sandbox will greatly simplify the task. Gossip, Sandbox? No, I don't know Sandbox. Okay, this book's like 15 years old. One thing I've learned is that when I write my textbook opus, I will not make reference to any particular software programs. I will just say, use the latest software available. Anyway, I'm sure there is some very nice graph theory software available, but I'm going to use just GeoGebra because I love it. It's free, it's web-based, it's basically pretty good. So look at this preparation I put into this. Here is 10A. And what am I supposed to do? What are the directions? Produce an isomorphism for the pair of graphs, or explain why the two graphs are not isomorphic. Well, I'm going to interpret this pretty loosely. I'm going to either determine that these graphs are not isomorphic, or I'm going to determine that they are, and then I'm just going to wave it away. And I guess here I reproduced the graphs in the exact way that they are in the book. But just like, can I just like stop already? Like, duh, done. Like, these two graphs are isomorphic. And let the isomorphism be determined by, they're in the exact matching position and look exactly like each other. So done. That was like, anyone could do that. A simple child could do that. Here we have something I think much harder to do in your head unless you're very smart. I'm not. I mean, to me this is one of these just like straight up IQ tests. Like, can you just like manipulate a million things in your mind? I can't, but I can drag things around. So are these two graphs isomorphic? I honestly have no idea, but I'm about to find out. And I got the feeling that the answer was probably no. So drag, 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 drag. And this is what I got. Oh, take it back. the freaking things are totally isomorphic. Well, that was a surprise, and now I win. So I'm sure there are many isomorphisms because these graphs have a lot of symmetry. But anyway, that's one of them. So are these two graphs in problem, whatever this is, 10b isomorphic? Yes, isomorphism as indicated by the vertices that are obviously matching each other. Okay, woo! This one, significantly harder. I think the first 5 years I tried to teach this topic, I did it without any software and just tried to do it in my mind or something. I don't know. Here, let's see. I'm going to make one of these look like the other one. I very, very vaguely recall that these two graphs are isomorphic. But, oh, watch this. I feel like I'm just so much smarter than I used to be. Is that right? No. That accomplished nothing. That accomplished nothing. Wait. I remember once getting up in front of... I remember once doing this and having a student kind of just get up there and... wait. Let's refresh. Let me actually focus for a second. And is this the original problem? Is this what it looked like? No. The original problem looked like this. Okay, this kid, I'll never forget his name, Joshua Fernandez, just was so smart, so much smarter than me. And one day he walked, I think I tried for 15 minutes in front of the whole class to do this with the Promethean board, dragging around. And he just walked up and he took the mouse and he just did magic. And it was just done. All right, so let me see if I can be him. Should have prepped this in advance. It's also possible that these aren't isomorphic. I think they are. Okay. So here's what I'm feeling. I'm feeling like C, D, E, and F are actually W, X, S, and V. Oh, something I should mention is, of course, these two graphs have the same number of vertices, 8. They have the same number of edges. Those can be counted. 8, 12, and 3, 4, 5, 6, 7, 8, and 12. What are the degree sequences? Well, in fact, these are just cubic graphs. They all have degree 3. So that's a good check. So are these isomorphic? I think they are. And I think I'm going to show you right now. But not like that, you're not. Okay, that was a dead end. Wait, instead of just dragging around randomly, I think I need to... might need to pause the video and really think about what I'm doing. But I don't want to, because I feel like that just ruins it. And those of you watching at home, you're probably just thinking, Mr. Rose, try harder. Why are you so dumb? Okay, hold on. Third try, and then I'm gonna pause the video and cheat. I want to kind of unwrap. Okay. If I unwrap E and F, then am I close? No. If I unwrap E and F, so I can do this. I need to find this little thing, but I don't see it. Who sees it? Who sees it? Help! Help! Okay, hold on. Pausing this for a second. Okay, it's 10 minutes later. I think I got this now. Here's the idea. The idea is this graph on the right. These are isomorphic. The graph on the right has this cycle of length 4, and this cycle of length 5, and this cycle of length 5, and this cycle of length 5. This graph on the left has this cycle of length 4, this cycle of length 4, and the big one of length 4. And also then there are these 5 cycles in here, B, D, E, F, H, B. A, C, D, E, G, A. Also, this one has a big cycle too. So you need to sort of do something with that. I don't really know what to do, but things are possible to do. For example, I have these sort of two adjacent 4 cycles. And so one thing I could do is make those 2 4 cycles adjacent by just dragging like this. This is not the elegant solution from this kid, but I can't remember what that is. So anyway, now are we almost done? We're almost done. Things are kind of like sideways though. So A and B are kind of eventually going to be T and W. So anyway, I think I'm almost done here, right? Maybe I need to drag those, and then did I say I was done with this? Is that done, or have I gone in a big loop? Hold on. Going back a second, because I feel like this is now almost done. So hold on. Let me just rotate everything sideways. I'm disgusted by my lack of elegance here, because I do think there are like 10 seconds worth of key drags that could accomplish the same thing. But anyway, I think I still win because what now? D is going to go here and F is going to go here. And have I just done it? Yeah, I just did it. Alright, so not so impressive because I wasted 10 minutes of my life thinking about it and I still didn't do a great job. But I have shown that these 2 graphs are isomorphic, and here's the isomorphism. Okay, what's left? This last one, and I feel like here the answer is they're just not isomorphic. After all, this graph on the right here is just the cubic graph. Like, this is just a cube. This is no cube here, man. And in particular, you know, there is a cycle of length 5 that goes from B to D, and BD, DE. Oh man, boom, boom. BD, DE, 3, 4, 5. And there just is no cycle of length 5 on the graph on the right. So they both have the same number of vertices, they both have the same number of edges, they both have the same degree sequence, which is they're both cubic graphs, which is to say every vertex has degree 3. But this is like literally the cube. There are 4 regions, they all have degree 4, but here is a region of degree 5, or maybe I should say there's just a cycle of length 5. Okay, so what did we conclude? Isomorphic, isomorphic, took me forever, very hard. Not isomorphic. I found a property that one has and the other doesn't. Alright, so am I almost done with this homework? I think so. This was yes, this was yes, this was yes, and this was no. Alright, what more did I have to do? What is this? 12C. Given any sequence of natural numbers arranged in decreasing order, there may not be a simple graph with this degree sequence. However, it will still be possible to construct a graph with this degree sequence. Okay, this is very misleading. That's because given any sequence of natural numbers arranged in decreasing order, is there always a graph for that sequence? No, because, for example, as we proved in your previous homework, you cannot have an odd number of vertices of odd degree because of handshake. And so, for example, consider the sequence of non-increasing, you know, that goes like this. I don't know, 3, 1. Okay. I mean, that's kind of stupid, but no. What am I talking about? 3, 1, 3, 1, 1. Say, boom, 3, 1, 1. Well, no. You absolutely cannot make a graph, simple or otherwise, with that degree sequence because the sums of the degrees of all the vertices has to be twice the number of edges. And so here, if this is 5, then we have a contradiction. All right, so this was a false. This was a true-false question. This was number 12, and the answer is false. However, it's kind of leading towards a question which is, okay, what if the degree sequence is or sort of doesn't violate a handshake. So now I'll ask a follow-up question, which wasn't really in the homework, but is certainly an obvious question, which is, give me a sequence of numbers such that the sum of all the numbers in the sequence is even. Is there always a graph for this? Well, there's definitely not going to be a simple graph. For example, 4, 2 is just impossible. Because I can't have a simple graph with just 2 vertices where one vertex has degree 4. So if the answer is there always a simple graph, then no. But is there a multigraph here? I feel like just yes, right? Because, well, what can we do? Connect these, and then, connect them again, and then, there we go. So we have to just kind of imagine, like, if you give me any sequence, I don't know, 5, 4, 4, 2, and 1, say, can I make a multigraph of this sequence? Because the sum of all the numbers in the sequence add up to an even number. And I think the answer is just yes, right? And it's not too hard to see this. Giving an actual proof might be somehow hard or something, but I mean, basically, I think here's what you do. You take all the vertices of even degree, and then you take all the vertices of odd degree. I'm outlining a constructive proof of a multigraph from any non-decreasing sequence for which the sum is positive. Well, if the sum is positive, is even. If the sum is even, then I partition it into the even numbers and the odd numbers. If you take the set of odd numbers, well, there must be an even number of them. So here, I just kind of, do it, man. Like there's a 5 and a 1, right? So let's just let this be the vertex of degree 5, and this be the vertex of degree 1. Well, by adding an edge between them, so this is what you do, right? You take the odd, this is what you do. You take the odd degree vertices, of which there must be an even number. Then arrange them in pairs, arbitrarily. Connect an edge between them. Well, now you are left with vertices, all of which require still an even number of edges incident with them. And then you just do loops. So this kind of like a lame way of doing it, but jump, and then jump. So this is a graph which matches up with here. Should we do another one? Let's do another one. That's like maybe like harder or something. So let it be just like, I don't know, 7, 5, 4, 2, and then like 1, 1 or something. Well, okay, so I have 6 vertices. 1, 2, 3, 4, 5, 6. First we take care of all of the ones of even degree. So boom, the 7 and the 5. Boom, the 1 and the 1. And now we just loop it up. Cha, degree 7. Cha, degree 5. Cha, degree 2. Boom, boom, degree 4. And then we're just done. So yeah, there we go. That sequence is called graphic, if it satisfies this. Okay, if two graphs, I think I'm using that. I think I'm using that term right. So okay, if two graphs have identical degree sequences, then they are isomorphic. Certainly not. Certainly not. Well, okay, this is kind of giving away a later problem, but well, we've already seen how this is kind of like not true or something, right? Because here is a graph. This is a graph with degree sequence 3, 3, 2, 2, 2, but 3, 3, 2, 2, 2. But now I'm going to make a non-isomorphic graph with degree sequence 3, 3, 2, 2, 2. Okay, well, I probably can't do this in the cool way that I want. Wait, maybe I can. Oh boy. Uh-oh, I think some people are coming upstairs, but I don't want them to. Is that just the same graph? If so, that's going to be embarrassing. 2, 2, 2. No, it's of course not. But I need there to be what just happened? 2, 2, 2, 2, 3, 3. So I need this. But then that's just the same graph again. Sorry, Theo, I can't. I'm kind of making a video right now. My 1-year-old just wanted to play with me, so I really need to wrap this video up. Okay, just let him in, just let him in. Okay, well, the cheese ball way of finishing this, which kind of ruins a later problem, is to just do the following. 2, 2, 2, 2, 2, 2, and then... What do you want? Oh, you want to give me the top?
Yeah.
Okay, thanks. Okay, Theo's gonna go color in the back. So yeah, this is a graph, this disconnected graph, which is also a multigraph, which has degree sequence 3, 3, 2, 2, 2. Okay, are we almost done? Please, are K6 and K3 are K6 and K3 isomorphic? Dude, come on. You want me to help you with this? Okay. Okay. My son is going to do some choreo on the backboard while this video is happening. Okay, come on, K33. First of all, I mean, how many edges even are there in K33? Like, probably 9, right? And yet, how many edges are there in K6? I bet not 9, because there are 6 choose 2, which is 15 edges. Is that right? That's kind of embarrassing if I'm wrong. 6 choose 2 is, yeah, that's right. It is 15. Okay, so it's just certainly no. That was a dumb problem. Okay, suppose G and H are regular, simple graphs with n greater than 2. Bring in some purple. Then are G and H isomorphic? G and H isomorphic. Suppose G are regular, simple graphs with n greater than 2 vertices, where each vertex has degree 2. Okay, so basically, if every vertex has degree 2, what's the classic graph where every vertex has degree 2? The cycle graph. And so you're probably thinking, part A, yeah, purple. You're forgiven for thinking that the answer might be yes, because I don't know, if you give me like this graph of degree, Theo, okay, if you're given this, here's red. If you're given this graph of degree, if you're given this graph with 4 vertices where every vertex has degree 2, you know, you're probably thinking it's not possible to make a non-isomorphic graph, but you are forgetting connectedness. It's not necessary. Well, in this case, this is a bad case. Yeah, but 6. Yeah, that's okay. I'm his little top holder. Okay. So what was I saying? Yeah. So consider C6. That's what I wanted to say. 1, 2, 3, 4, 5, 6. So here's a graph where every vertex has degree 2, 6 vertices. But of course, this is also a simple graph where every vertex has degree 2, 6 vertices. Aha! What was that question I was asking? Regular? Check. Because every vertex has degree 2. Simple? Check. With n greater than 2 vertices? Yep. Every vertex has degree 2. It's kind of redundant from saying regular. Are G and H isomorphic? The answer is no. So in other words, provide a counterexample. But now, suppose part B kind of gave away how you're supposed to... Oh my gosh. Part B kind of gave it away, because part B says, well, what if they have to be connected now? And I think the answer is, now the answer is yes. So how can we do a proof? Let's just do an extremely sketchy proof. I have greater than 2 vertices, so at least 3. They all have to be degree 2. They all have to be connected. So without loss of generality, these two need to be connected to each other. But then, like, every vertex has got to be, it's just like, man, you just do it, right? However many vertices there are, you know, you just got to connect them, and they have to be connected together. So the only way, I guess the claim is something like, the only way for a whole bunch of vertices to all be connected to each other and of degree 2 is that they are together in one big cycle. And so if you give me n vertices, the only connected graph is the cycle graph. Okay, video quality plummeting. Let's just be done. Are we almost done? 2 more problems to go. Let G be a simple graph with n vertices if G has degree sequence D1, D2, Dn. What is the... Oh my gosh. Theo! If G has degree sequence D1, blah, 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 what is the degree sequence of the complement graph? Okay, I don't even totally know how to do this problem, so I'm not going to try very hard. But here's like a graph, right? Maybe we'll do that one. What does the complement look like? The complement graph looks like this. So, okay, so what were the degrees? The degrees were 3, 1, 2, and 2. And what are the degrees of the complements? Well, 0, 2, 1, and 2. So, I mean 1. So what do you notice? Well, of course, that's the way I encourage you to think about the complement graph. It's just the graph which adds all the edges. In other words, it's the graph which, if you superimpose the complement graph and a graph, you get the complete graph. And in the complete graph, every vertex has a degree n-1, where n is the number of vertices. And so that's pretty much what's going on. So if you look back at this problem now, what do we have? We have we have n numbers in this sequence, and therefore the graph has n vertices, as it says. If the graph has n vertices, then in Kn, the degree of every vertex is n-1. And so therefore each vertex in the complement graph is going to have like the complement n-1. So in other words, here's the answer. The degree sequence of G complement is going to be, of course everything reverses, n-1 minus d sub n, comma n-1 minus d sub n-1, all the way out to n-1 minus d sub 1. In other words, the it's going to be the same sequence. I don't know why that looks so dumb, but it's going to be the same sequence in reverse, but with every degree being the difference and n-1. Okay, that was a terrible explanation. Don't care. Find an example of a graph G that's isomorphic to its complement. Well, a graph G that is isomorphic to its complement. So I need to do it with 4 vertices. Okay, I think I just did this one like by accident a minute ago. Here's a graph. Cha, cha, cha. What is the complement graph? The complement graph is that. And it is, in fact, isomorphic to itself. A down, B to go. How about if there are 5 vertices? Watch this. Is that right? Yeah. So that's a disconnected graph with 2 components. What does the complement look like? The complement graph, every one of these vertices is so it's like, well, I bet that's just like wrong, right? Yeah, that's just like wrong. Okay. Hold on. Maybe if I do. Okay, well, let's be smart for a minute. What do I know about what do I know about the complement? If there are 5 vertices, then there are 5 choose 2 equals 10. So first of all, this was just totally stupid because this had no chance of being right because I had the wrong number of edges. But now maybe it's right. And I bet it just is, right? Yeah. I bet this is just, I bet like almost anything I do just kind of like works now. So let's see. This one goes here and here. This one goes only here. And this one goes to those two. And am I done yet? No. This one is going to go here. So is that... but I just like failed because these two are not isomorphic. Okay, wait, hold on. I need to think this through a little bit more carefully instead of just being like stupid or whatever. And then I need to be done with this video. Find a graph which is isomorphic to its complement. Hint, use exercise 18. Maybe I should use exercise 18, everyone. If there are 5 vertices... There are 5 vertices. Okay, let's be like an actual mathematician now. There are 5 vertices. So I have a graph with 5 vertices. Alright, well then, it's going to have a certain number of edges. How many edges could it have at most? 5 choose 2, which is 10. So if a graph and its complement are going to be isomorphic, then of course they have to have the same number of edges, so they have to each have 5. So if there are 5 total edges, this is going to apply to part B and part C. Then there, so 10, 5 edges. Then, of course, I don't know if this tells me anything, but the sum of the degrees of all the vertices has to be at least... has to be exactly 10. Okay, and then... So I'm going to use the degree sequence to help me with this, I guess. And then also, for any degree sequence and its complement written back-to-back or whatever, it's going to be... The sum will be 9. So can I just maybe like do... So maybe I'll just do something like 4, 3, 2, 1. No, the sum's not going to be 9. The sum is going to be 4. So then, so I need to find a sequence, 7, 8, 9, 10. I need to find a sequence such that... what the hell am I doing? The sum of the degrees... There need to be 5 total edges. So the sum of the degrees of all the vertices has to be 10. Oh, of course there's supposed to be 5 things in this sequence. So 3, 3, 2, 2, 2. But then that's just not going to work. So, because I need it to be symmetric. So maybe I do want 4. 4, 3, 2, 1, 0. Ah, that's just going to work, right? Because then the reverse will be 4, 3, 2, 1, 0. Okay, so that tells me what I need to do. 1, 2, 3, 4, and 3, and then automatically this is 2 and 1. Okay, so I bet I just got it now, because I bet I just got it now. So let's just see. I'm gonna just do it on the same spot, although that's potentially confusing. 3, 4, 5. Oh man, it's so late. So this one's gonna be, no, first of all I did the wrong graph. Oh geez. This problem is turning into a giant failure. I'm gonna pause this video for a second. Okay, I'm back. I think I had the right gist. I'm back like 1 second later, so I haven't actually like done any more thinking. But I guess it needs to be like this. If it's a simple graph, then if that's 3, then that has to be 0. Because if there's a vertex of degree 3, then there has to be, what did I say? If there's a vertex of degree 4, then there has to be a vertex of degree 0. And if there's a vertex of degree 3, then there has to be a vertex of degree 1. So this is actually exactly what I had. I think I just like somehow did a terrible job of actually doing it. Oh, no, I see the problem, because you can have a vertex of degree 4 and also a vertex of degree 0. So I take it back. So this has to be 3. I don't know how to do this problem. It's actually really easy, but I can't focus right now. So I might just like give up or something. There are various threats being made at me downstairs. 6. Okay, so I guess this is just gonna work. This is the dumbest way. I've done this problem in the past with just like no thinking, but now there's a certain amount of thinking going on, and it's just not helping. All right, so I bet that's just right now. Okay, let's go. This is going to go here and here. This one is going to go only here. So I took care of like this one and this one. This one is going to go here and here. And I think I just fail again because these two graphs are not isomorphic. All right, this is just like an easy problem, but I'm just being really, really dumb. So I guess I'm just gonna give up. But I had to find like 2 examples of this. Find an example of a graph is isomorphic to its complement. I feel like this just shouldn't be hard. I feel like this should be so easy, but for some reason I can't find one. I have all this fascinating stuff here, but nonetheless, I can't even come up with one example, and I'm supposed to be coming up with 2 examples. So anyway, you try, and we'll end this video with me failing, which is how the videos usually end. And that's all I got. It started so strong. Let me try one more time. Okay, I'm back. One example came to me immediately, which is just the cycle graph C5. Duh. This is a graph, and this is what's missing in K5. And of course, this star just is also C5. So this is a graph, this is complement, they're isomorphic to each other. For the other example, I struggled for a while, and then I just went back to the theory. The theory is, like I was doing before, I am using exercise 18. I need to find a graph which has 5 edges, so its complement will also have 5 edges. I need the sum of the degrees of all the vertices to be 10. So that was guiding this construction of this degree sequence. I then had to make my degree sequence symmetrical because I know that the other degree sequence must be the same thing if the graph is to be isomorphic. And okay, so anyway, then after just playing around through a couple of possibilities, I just like found it. So here it is, and now I'm just gonna show you that the complement of this graph is isomorphic. How? Let's see, there's going to be one of those, and then there's going to be every diagonal except for that one. So jump, 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 and jump. And, well, what is this? This is just a triangle with 2 things sticking out of it, and this is also a triangle with 2 things sticking out of it. So, woo! I win eventually. These two graphs are these two graphs are complements of each other, and they're isomorphic. These two graphs are complements of each other, and they're isomorphic, and these two are not isomorphic to each other. So I really did do 19B and 19C. Woo, video over. Goodbye.